Alright, welcome. So the summary of the earlier lectures was we did introduction and constraint optimization, classification, transformation, and yesterday we started the necessary and sufficient conditions. The way we are doing it, we are going to first do the first order necessary with equality constraint, then we'll do first order necessary with inequality constraints, and then we'll go to the second order and the sufficiency conditions, which will happen next week. So we gave the theorem for this. What was the theorem? Can somebody recall? If x star is a constraint, is a local minimizer of the problem, the constraint optimization with equality constraint, then it should satisfy the constraints ai of x equal to 0, and the b was gradient Sakir. The gradient of the function is linear combination of the gradient of the constraints. The constant in front of the constraints were referred to as the Lagrange multipliers, right? That is what we did. We did the first problem very easy, second slightly harder, and the third one we were doing which we couldn't finish yesterday. So we're going to finish that part. So once we had solved this second problem, we had ended up with these two set of equations. The first equation is a set of underdetermined equations, which means they had infinite solution. The second was a fully determined system of equations because H is n cross n, A was r cross n. Everybody recalled from yesterday? Okay. So then we did was we took this x here and substituted it in here, and we ended up getting this. So the question which we had stopped yesterday was, when is this matrix invertible? Because this is a square system, everybody agrees, r cross 1, r cross n, n cross n, n cross r. So it is a r cross r matrix. It's a square system of equations, fully determined. It will have a unique solution when it is invertible. So we had to prove its invertibility by using the two facts which are given in the problem. The first fact was that H is symmetric, positive, definite. And the second was that A is full row ranked with R less than N. So it's, rank is R. Right? So those are the two things we have to prove. To prove it, we said we'll do it in two phases. So the first proof we wanted to do was if H is SPD, then we prove that H inverse is SPD. So this is coming from linear algebra. I don't know if you have proved it, but we'll still, so that you get a little more oiled in this kind of proofs, we're going to repeat it here. Okay. So what is the definition of a, symmetric, H is equal to H transpose. By the way, positive definiteness is invariably studied for symmetric matrices. It is very rarely that you can say that you want to see an unsymmetric positive definite matrix. So that's another story. But when you say a matrix, and don't write it PSD, don't write positive symmetric definite. The symmetric always comes in front. So that's why we write symmetric positive definite. When the S comes in the middle, it's usually referred to positive semi-definite matrix, right? So just keep that nomenclature in mind. So what is positive definite? So if Y transpose HY is strictly greater than 0 for all Y not equal to 0. Well, if it is equal to 0, then it'll become equal to 0, right? So usually this doesn't bother you much, but we still carry it. When it's positive semi-definite, then it's something you have to worry about for all Y. Basically, you take any vector and multiply the matrix is on the left and on the right, and the scalar quantity which you will get should turn out to be positive. That is what is positive definite. If the Y is 0, then the whole thing will be 0. It will never be positive. So, that predicate is usually just for the sake of it we are carrying. So how should we prove? So we have to prove that H inverse is positive, semi-positive definite. So to show this thing is greater than 0 for all, this is the sign for all. Everybody agrees? This is what we have to show. So what we'll do is, we'll start with, since it says for all Y, I will start with any general Y. I can pick any Y, So say you pick any y. I mean, you can also call this as y1 if you want, because you're making a specific y here, right? So what the next step which I do here is I can write, we can find a z, or let me just call it z1 is equal to h inverse of y, or y1, or let me say y1. Let me just carry this specific y. Can I write this? Can I find a z1 given a y1, an arbitrary y1? Can I find a z1? Yes, because h is invertible, so I can always find. So I'm going to put this back into this equation. So we'll say to show, instead of y I will put, so this would imply y1 is equal to h times z1. Correct? I just switched the sign. So I'll substitute into this to show, instead of y transpose I'll write h z1 transpose times h inverse. Instead of y I will write h of z1. We have to show this greater than 0. This, the rest predicate is still being carried. Right? So or to show z1 h transpose h inverse h z1 greater than 0. Yes? Yes or no? Or to show z1 transpose h z1 greater than 0. H and H inverse become identity. H transpose is H because it's a symmetric matrix. Now, is this true? Why is it true? Because H is positive definite. This is true if Z1 is not equal to 0. That's the definition. So, is Z1 not equal to 0? Why?
H and Y both are not.
So we'll just do the negation of it. So say Z1 is equal to 0, which would imply that Y1 is H times a 0 vector is 0. So which implies Y1 is equal to 0, which is conflicting with the fact that this Y1 which you had picked was not equal to 0. So this is not possible, hence proof. Ask me. If you're confused, don't, it's not nothing to do with you. Ask me, what's the doubt?
So H is like it will be H transpose there.
H transpose will become H because H is symmetric as well. So I just put it as H. Everybody okay? So now you try to do the harder part. What was our goal? Our goal was to prove that this guy is invertible. I said instead of proving invertibility of this, we are going to prove that this is symmetric positive definite. Hai na? SPD. So we first proved this. So now we'll do the harder proof. So this was the proof 1. Okay. So we'll do the second proof. Proof 2, we have to, so if, here we are saying if H inverse is SPD and A is full row rank, then this thing A times H inverse A transpose is SPD. This is what you have to show. So, how should I approach this? Everybody getting comfortable? This is the second, this is now third short proof which we are doing. One we had done a week ago or last week whenever we did the class. So how should we approach it? How do we prove that this thing is symmetric positive definite?
Do the same thing again.
Same thing we'll do, है ना? So we'll do the same thing to show Y transpose A H inverse A transpose Y is strictly greater than 0 if Y is not equal to 0. The same thing we'll do to show. So we'll say true for, say given a y1 which is not equal to 0. So now what should we find as our z1 to make things easier? This is the one which is bothering me. And H inverse inside, we know this guy is symmetric positive definite. So we only see, so we'll say we can find Z1 is equal to A transpose Y. Y1, sorry. Since we have picked up one specific Y1, we can multiply that Y1 with A transpose and we can always find a Z1. Correct? So what do we have to show? To show this is A transpose Y becomes Z1. This is Y transpose A, which is A transpose Y whole transpose. So that will be Z1 transpose. To show Z1 transpose H inverse Z is greater than 0, equal to 0. Again, is this true? Yeah, if this is true, if Z1 is not equal to 0 because H inverse is SPD. The definition of SPD was multiply with any vector on left and right and you should get a positive quantity. Everybody with me? Okay. So let's do further now. We have to show that Z1 is not equal to 0. All right. To show Z1 is not equal to 0. So say Z1 is equal to 0. So we are again going to do contradiction like we did earlier. So Z1 is equal to 0. Then this would imply that A transpose Y1 is equal to 0. Now what can we say from here? So let's write it down. So many of you have already seen it. So we'll write this as A1 transpose, A2 transpose all the way till AR transpose times Y1 first element all the way to Y1 rth element equal to 0. What is A1, A2, AR? These are the rows of the A matrix. Since I transpose them, I wrote them as a column vector. This transpose should not be there because A transpose was A1 transpose to AR transpose, where these were all rows. Once I do the transpose of that, then they just become the columns. Correct? Now this would imply that Y1, the first element A1 plus all the way till Y1 rth element AR is equal to 0. We know that A is full row rank, which means that these vectors are linearly independent. The sum of linearly independent vectors is equal to 0, implies that the constants in front of them are 0. So this was, since A is full row rank which would imply, I'm not writing this, that A1 through AR are linearly independent, which would imply that Y1, the first element, all the way to Y1, the rth element is equal to 0, which would imply that Y1 is equal to 0. Again a contradiction, because we assumed here that Y1 is not equal to 0. Hence Z1 is not equal to 0, hence proved. Yes, everybody with me? Comfortable with small proofs? We'll do another proof now. Today is proving day, because yesterday we did numerical examples. So we'll now prove the theorem which I have just erased. Okay. So the last thing which we do today is, usually I use star for a big heading, dash for a smaller, and a double dash for a subheading, if you're confused why I'm putting dash. So proof of theorem of first order necessary condition for equality constraint problem. Okay, now we're going to go back to the proof and try to convince you that why this is true. So if you recall, the optimization problem was minimize f of x with respect to x, f going from Rn space to R1 space, subject to ai of x equal to 0, I going from 1 to R. If you also recall the theorem, the hypothesis says if x star is a minimizer of the above problem and is a regular point of the constraints, then the first thing we had to show was that ai of x star is equal to 0, and the second thing we had written, this is all written, I'm just writing so that it's there in front of you. I going from 1 to R, lambda I star ai, gradient of ai of x star. Yes, this was the theorem. So we're going to prove this now. To prove it, do we have to prove the a part? Yes or no? It's obvious, no? If it's a minimizer of the function, it has to be a feasible point. If it has to be a feasible point, it has to satisfy the constraint. So A is obvious. We don't prove the A part. So since A is obvious, or if somebody asks you, you can say it in words what it means. But we are going to prove the B part. To do the B part, what we're going to do is we are going to build a space which is spanned by, I assume you know the span of a vector space, rank, nullity and all that. I assume you've studied, right? If you're not clear at any point of time, you ask me. Okay. So we say let this be the space which is spanned by the gradient of the constraints, which is gradient of ax all the way till gradient of a1 through gradient of ar of x star. What is the meaning of a space being spanned by a set of vector?
Any vector can be represented as a linear combination.
Correct, correct. What's your name? Uma Mahesh. Okay. So like Uma Mahesh mentioned exactly correctly that when you say a vectors are spanning a space, which means any vector in that space can be written as a linear combination of those vectors. So which means that if there is a vector somewhere here, this will be a linear combination of this. So right now I'm not writing this. Now what we do is we take this guy, the gradient. This is, I'm showing this in a two-dimensional space. Of course, this is n-dimensional, which can't be visualized, right? we'll take the vector of the gradient of f, which would be any vector in the space. We don't know what direction it is. Let's say it is this. It could be any direction. Just for the sake of explanation, I'm showing it. And we project it down onto this space spanned by the gradients of the constraints. We do a perpendicular projection. You can do an oblique projection as well, but we are right now doing a perpendicular projection. Okay. So this is gradient of fx star. This is becoming a triangle in an n-dimensional space. I'll call this as the D vector. This I'll call this as the projection. Using the same terminology I wrote so that there is no confusion later. Yeah. So this is the projection and this is the D vector, which is connecting the two. You're taking this vector, projecting onto the space, hence the name projection. Huh? So by the triangle inequality, what can we say? This vector plus this vector is equal to this vector. Correct? So I'll write that down. So I'll say the projection vector plus the D vector is equal to the gradient of fx star. Okay, let's be more explicit. Okay, so let me write what this projection vector is. So I'll just write the opposite direction. So gradient of fx star. So the projection, how can I write the projection vector? In terms of the gradients of A, the linear combination. And the constants which I am going to use for the linear combination, I am going to refer to them as lambdas. I can refer to them at anything, but since I'm trying to come to this form, I refer to them as lambdas. So I'll say this is lambda 1 gradient of A1 x star plus all the way lambda r gradient of AR of x star. This is my projection vector because it is in line in the space spanned by those vectors plus the D vector. Everybody with me? So which also means that gradient of fx star is equal to summation of I of 1 through r lambda I gradient of AI of x star plus D. Everybody with me? Now what should we show? We need to show if x star is a minimizer, then D is equal to 0. Correct? Everybody with me? So we need to show if x star is a minimizer. I'll not say a minimizer. What should I be more explicit? A local minimizer, which means in the neighborhood I am gives the smallest value. If x star is a minimizer, then D is equal to 0. To be able to show this, I will rather prove the contrapositive. What is a contrapositive? It's the negation of the whole thing. So we'll say if D is not equal to 0, then x star is not a local minimizer. You can fill the local minimizer thing. So this is what we're going to prove. So since D is not 0, we'll say, let's say we find the direction vector E is equal to minus D. This is some direction going from x star. You are at some point x star in the space and now you want to move in this direction p vector, which is the negative of the d vector. Let's say what I'm going to do is take the inner product of this direction vector with this equation. Okay, so once I do this, so what's the inner product? This times this means this transpose this or this transpose this. It's the same thing, correct? So I'm going to write this as gradient of fx star transpose times d is equal to summation of I is equal to 1 through r lambda I gradient of ai of x star transpose times d and minus this. Correct? Yes or no? Norm squared is just the inner product of the two vectors. Norm square is d transpose d, or norm is square root of d transpose d, hence the square there. Everybody with me? Okay. Now what do we do? Any ideas? Think. How do we reach to our result, or how do I simplify this further? What is it that I have not used until and I assumed and I have not used in my setup? With p, sorry. Yeah, it's minus d. So this is minus here. Everywhere is minus. I took an inner product with the p vector, which is minus d. It doesn't matter the sign. But I want to simplify this further. So what should I do? In the setup, what kind of projection I have done? Yes. What's your name? Sanjana. Seems Sanjana is with the class the most. But anyways, so it's an orthogonal projection which I have not used. It could have been an oblique projection as well, right? If it was an oblique projection, the triangle inequality would still have been valid from the triangle law. So I have not used the fact that this is a 90 degree. This is a 90 degree, which means that D is orthogonal to the space, which means that D is orthogonal to all of these vectors, because all of these vectors are lying in this space and I am going orthogonal to it. Correct? So what we have not used is the fact that the gradient of ai of x star transpose d is equal to 0. This is something which is there in my setup. Correct? So you can write this since orthogonal projection. So substituting this in 1, we get that the gradient of fx star times d minus is equal to minus norm of d square. Correct? This term becomes 0. Or gradient of fx star transpose p is negative. P was the negative direction, the direction which I was going. This is D is not equal to 0. First of all, which we have assumed, it's an orthogonal projection. So D is, if D was equal to 0, you didn't have to do anything. It was already true. So D is not equal to 0, which means this thing is explicitly less than 0. It is not less than equal to 0. Correct? Now let's mark this as 2 and write the Taylor, because I was at x star and I was going in the direction P. So if I have to write the Taylor of that, so fx star plus P is equal to fx star plus gradient of fx star transpose P plus order of norm of P square and so forth, right? Everybody remembers Taylor? I've written the first order approximation, first degree approximation. I'm carrying only the gradient term. If I was carrying another term, the Hessian term will be the second degree approximation. So let's say for the argument I ignored this, the smaller terms, although Necc may have done this in the proof of the unconstrained optimization necessary conditions, the gradient is equal to 0. We actually say that this term dominates than this term. You can always, so this can be negative and this will be positive, so the whole thing can always be shown to be negative. This is how we prove. But in case you've forgotten all that, I'm not going to recall. Just ignore the smaller terms because they are tending to 0. So let's try to look at this term. So this would imply gradient of fx star transpose p. P is carrying both the direction and how much you're going in that direction. It's not a unit vector, so just remember that. This is equal to fx star plus p minus fx star. Correct? I ignored the smaller terms. So now if I substitute this, then what do you get? F of x star plus p minus f of x star is less than 0, or this thing is less than f of x star. Yes? Yes or no? Yes. So which means that I was at x star and I went, if I draw a smaller circle around it, a hypersphere, and I went in the p direction, I get a reduction in the function value, which means I am no longer a local minimizer. Correct? Implies x star not a local minimizer. This is what we had to prove. If d is not equal to 0, x star is not a local minimizer, or x star is a local minimizer, so d is equal to 0. Everybody with me? Okay. There is one more thing which we had to be careful about, which I have put it under the rug kind of a thing. One thing was, of course, ignoring the smaller terms. You can be more rigorous and carry the smaller terms and still prove it, but we are not worrying about it for the moment. At least in a third year class at this level, I'm not worrying about those things. But there's something else which we should have been careful about. Can somebody think what is it? Which I'm going to tell you now. Correct. Who answered that? Aviral? Yeah, okay. Aviral, Sanjana, Uma, Mahesh, and Shaurya. Correct. Okay. Alright. So, as Aviral just mentioned, what we have not shown is, was P a feasible direction or not? If it was not a feasible direction, then what are we trying to prove even? No? If I am this at an x star, and I'm going in the direction P, which is equal to P is equal to minus D, I can't even go that direction if it is not a feasible direction. If it is leaving my feasible region, let's say it's at the boundary of the feasible region, then all this analysis will not carry forward, because the minimizer is checked inside a feasible region, the intersection of the neighborhood and the feasible region. Remember the definition which we talked about, the classification thing. So now, as he mentioned, we had to show that P is equal to minus D is a feasible direction. To show that, our best friend for this class has been Taylor. It's going to be Taylor for a very long time. So we are going to use the Taylor approximation now along with the constraints as well. Okay. So let's say I pick, without loss of generality, I pick any one constraints, AI. So I'm at AI of x star plus P. So here we did the Taylor on the F. Now I'm doing the Taylor on the constraints. So I can do on any constraint. So I'm writing AI. So this would be AI of x star plus gradient of AI of x star transpose times P plus the smaller or the higher order terms. Correct? Everybody with me? Now what do we know in this? This thing is definitely 0 because x star is a feasible point. Otherwise there is no point studying whether it's a minimizer or not. The domain itself is defined by the feasible region. For the new point which I am going to reach, which will be x star plus p, this point should also remain inside the feasible region, which means that this guy should also be equal to 0 for that, so that the direction is feasible. Now you're starting at x star, going in the p direction only because you're inside the feasible region. So this is given to be 0. This we need to be 0, and if we ignore this, we need the gradient of ai of x star transpose p to be 0, or we need gradient of ai of x star transpose times d equal to 0, which is given. The orthogonal projection is ensuring that. Is everybody with me? Comfortable? Okay. So this time, like I said, I have taught the reverse direction. I gave you the necessary condition. Then we did 3 examples. Then I proved you, so that you can appreciate and not get bored with the proof. Okay, so we'll switch gears and move to something new now. New in the sense, we'll move to the case of inequality constraint. We have time. Okay. So we were in the section of necessary and sufficient conditions, and what you saw with me was first order necessary for equality constraint problem, and now what we want to see is first order necessary for inequality constraint problem. Okay. Now let's, well, technically you can avoid this completely. Why? You can always convert inequality constraint to equality constraint. So, but the reason there is a theory related to this is that sometimes their inequality constraints are so many that you increase your search space. So you don't want to do that because the number of constraints will become larger. The x will become larger because the constraint will vary and the dimension of the problem increases. To avoid that, we do. So we'll first write the theorem and then we'll do problems on this. We are not going to prove it. You know? So this much proof is enough for the moment for you. Once we finish this whole theory, then we'll start linear programming, and there again a proof will come before the algorithm comes. So this says if and this is something which is a buzzword, and I should write the spelling correctly. So this came after name of 3 people, Karush-Kuhn-Tucker conditions, or which also referred to as the KKT condition. So if somebody asks you, have taken optimization course, then they will say, okay, you know what a Lagrange multiplier is. That is, for example, the very first thing which we'll ask. Do you know what are the KKT conditions? Because they become the foundation of everything. And like most things in mathematics, the people who derive it, or even in computer science, have you taken a walk in our faculty offices now? Have you come recently? Take a walk. We have put all the photos of famous scientists who have come up with certain ideas, and we have, in fact, Ranveer has done a nice job. The current head, he has thought over it and put the names based on somebody who works on a particular area. So outside my office is the photo of Gauss. Gauss was a German mathematician. He's called the Prince of Mathematics. He was 1777 to 1800 something. The amount of work which he did is so much relevant today in 2024 that is forming the foundation of all the analysis and function analysis we did. So anyways, this is something, but West has been typically biased towards Indians and not giving names to a lot of things which Indians in India have derived, you know, not being in US and finding something. So Professor Manindra, so this, you can count this as a joke, a break, so that wake you up. Professor Manindra Agarwal, who's now the director of IIT Kanpur, he was a computer science faculty at IIT Kanpur for a very long time now, and his 2 undergraduate students decided to do PhD with him, computer science, which is rare because you do bachelor's and move to US and do PhD. Anyways, they did, and they solved one of the open problems in computational science, in computer science. That's a different story, what that problem is. But now that theorem is referred to as theorem by 3 Indians. So that's very strange. You name them, no? Agarwal, something. So anyways, so this is Karush Kuntakar. So that was the side remark on this. So the problem says if X star is a local minimizer Okay, I should have written the standard form of, let me then write it, minimize f of x, f going from an n-dimensional space to a one-dimensional space subject to ai of x equal to 0, cj of x greater than equal to 0, I is equal to 1 through r, j is going from 1 through s, and is regular for constraints active at x star. So if you compare this with the case of only equality constraint problem, then of course you have the inequality constraints which are carried forward, and the regularity in the previous theorem was only for the active constraints, because that is what we told you, है ना? Only for the equality constraints because they are always active. What is an active constraint? It is on the boundary. It is exactly being satisfied with the equality. So these are all active, and some of the inequality constraint can be either active or inactive depending on whether you are at the boundary of the constraints or inside it. So it's saying it should be regular for the constraints that are active at x star, which means that earlier you were only carrying a1 through ar and showing them the gradients of those are linearly independent. Now you have to carry some of the gradients of the inequality constraint as well with you. Those are which are active at x star. So it will be a1 through gradient of a1 through ar and some c1, c2, c8, c10 gradients of those. All those set of vectors should be linearly independent. So that is what we assume. By the way, I have not given you the intuition about this linear independence thing, which I am going to give you next when we do the sufficiency conditions. This part I have skipped in the proof here. Okay. So assume that all that is given, it is a minimizer, then what should be true? The very first thing which should be true is ai of x star should be, it should be a feasible point, right? And cj of x star should be greater than equal to 0. J is going from 1 through s. This is obvious. If it is not a feasible point, why don't study about it? The third thing which will be equivalent to the B condition in the equality constraints would be, earlier you were taking gradient to be equal to the linear combination of the equality constraints. Now the inequality constraints will also play a role. So you will say there exist, this is a sign of there exist in mathematics. For example, this is for all, this is there exist. You write this and you put the opposite. There exists Lagrange, again Lagrange was French mathematician. Lagrange multipliers there exist Lagrange multipliers. We call them two types, lambda I star and mu j star, such that this is readable to you, this lower part. Gradient of fx star is equal to summation of the equality constraints gradient and summation of j going from 1 through s mu j star gradient of cj x star. So what did we have in the earlier case? We only had I need to just come for a second, spit, my throat is not good. So earlier we only had this, no? Gradient of the function is a linear combination of the gradient of the equality constraint. Now it is a linear combination of not just the equality constraint but the inequality constraints. We refer to with the equality constraints lambdas, with the inequality constraints we refer to them as mu's, right? So nothing changes here, but doesn't stop here. There are two more conditions which we are going to write. Not sure if we'll have time to solve a problem on this, but at least we'll finish understanding this. The other two conditions says that the product of the Lagrange multiplier with the constraint is 0. So it says lambda I x star times ai of x star is equal to 0, I going from 1 through r, and mu j star cj x star is again equal to 0, j going from 1 through s, and there is a E condition which says mu j x star is greater than equal to 0 with j going from 1 through s. So those are the 5 conditions, the KKT conditions which we call. So then the way we refer to these conditions is the first two conditions are called as the feasibility condition because we are just checking that. The C condition is referred to as the Lagrange multiplier condition because the Lagrange multipliers are coming into play into this. The D condition is referred to as the complementarity conditions. The complementarity means that there is a product or orthogonality between the vectors. So this and this products are 0. And this is referred to as the non-negativity condition because there is a non-negativity on the Lagrange multiplier corresponding to the inequality constraint. So again, those two conditions become 5 conditions. There is of course an elaborate proof for this, but I'm not going to go over this in class for you at this level. But applying this itself is a challenge, finding an analytical solution through this. What you would see 2 weeks from now when we start linear programming, this would be a starting point. We'll take the linear program, convert or simplify these conditions for the linear program. These are necessary conditions. They will become sufficiency in the linear program. Then we'll start our first algorithm. We'll say, how do we start an algorithm which satisfies these constraints upon convergence so that I can find a minimum. That's why this is the foundation of everything which we're going to do further on this. Is that okay? If you look at these conditions, can we make this simpler? Can we get rid of some conditions? Is there an extra condition here? Correct. Right. This is not needed because AIs are anyways equal to 0. It's a feasibility condition. In fact, this need not be true for all S. There would be set of CJs which will be active, which means there will be some CJs will be equal to 0, some CJs will be strictly greater than 0, the inactive one. The ones which are active, you would not need to satisfy this, but this will be needed for the ones which are inactive. So there will be a reduced set of equations which you work with. which we'll see when we solve the problem. Everybody okay? So what I'll do now is we have to go to the lab, of course, but I still want some feedback because I don't know how the class is going. I've taken 5 lectures, you've seen tutorials, you've seen labs. So just take a small chit of paper and just write on it what is going fine and what you would like to improve. Because you are so shy to tell me physically, so you can write it on a piece of paper. It need not be really big. Don't give me empty chits, hai na? Don't write fine or good. Just write something that this is going good. For example, the pace is going fine, but the problems need effort.
Can we choose a representative?
For
Convey
convey what?
Can we choose a representative among the class to convey our thoughts directly?
You can always do, but give the feedback now, right? I mean, you have a CR already to convey the thoughts, right? Why Vedanta, you're so special? Acha, good speaking skills. So I know that 5-6 people in the class are getting it. Sanjana, Aviral is getting the most because he responds the most. Shaurya, Atharv, Aviral, Sanjana, Uma, Mahesh, and Saket also is doing fine. But I don't know the weaker part of the students who are not getting it. So I need that feedback for them more than for you guys actually. If you feel TA is not doing a good job, you can tell that also. Although he's sincere. Very good. You can stop the recording.
Thank you.